Yeah. So hi everyone. Good morning. So my name is Victor. I come from a company called Acutronic Robotics, which is based in Switzerland. And I'm here today with you to share a bit of our journey on basically how we address the system integration problems through modularity and specifically using ROS. So the first question that I'd like to answer is, who is Acutronic Robotics? Because maybe some of you have heard about Robotics. We funded this company around 2014. At the time I was a PhD student, I dropped it out to start this company, and we started creating basically modules for making drones, aerial vehicles. It was quite successful. At the time we were doubling our sales every second month or so we grew pretty fast. And at some point we had this crazy idea of, well, can we actually extend our concept of modularity, these hardware devices, to any robot device like sensors and actuators? And so suddenly an opportunity came up, DARPA funded us, and we delivered some prototypes that indeed showed feasibility of this. Further developing the concept, we got a few offers, and eventually we got acquired by the Acutronic Robotics group, which basically was mainly funded by Acutronic, which is a big Swiss company with hundreds of employees. They basically do motion control, very, very precise motion control, and they make like huge machines like this room probably to measure like accelerometers and gyroscopes and radars. They've been doing this for like 100 years. Sony came up with us last year and supported us financially. So right now we, as well as the rest of my team, are basically pushing full-time modularity. And that's what we are doing. We're about 25 persons, mainly operating from Switzerland and Spain. And yeah, that's who we are. Now, system integration supersedes basically many of the things when it comes to building a robot. And this is something we've been seeing over and over and over throughout our whole process of building different robots, from aerial ones to actually robot manipulators. And actually, interestingly, programming robots has been a big topic of research for the last decade or so. Actually, ROS has showed how important that was, and thanks to ROS, actually we're all of us together today. ROS, I think, is indeed successful, and some may claim that it's going to be indeed the de facto standard for robot application development for the future and from now on. But honestly, our experience is that system integration goes way, way beyond simply programming the robot. I mean, according to some studies and statistics, roboticists, when it comes to fixing a real application, use about 70% of their time resources, not probably their time resources, on actually system integration, dealing mainly with the hardware and the software interface. And they do it over and over and over again for each one of the projects they have to tackle. So we ourselves basically started this modularity journey to address this particular problem. Why? Well, because if we compare actually the traditional system integration process, which is kind of like highlighted over here, you can see how the second step, integration of components, takes a big part of the graph. Now, if we look at how the modularity or the modular approach for building robots goes, we see that the second step before has been barely eliminated or completely eliminated in this particular case. And that is because by adding modularity, we can somehow solve some of the big problems within system integration, such as interoperability and dealing with complex hardware-software interfaces over and over again. By the way, all of these things are available, and these slides will be available, so I see some of you taking notes. This will be available, and some of these, well, all of these papers actually are publicly available as white papers, so you can see everything afterwards. Now, I'd like to share with you today a few of our, let's say, a few of the challenges we've been facing over the last years. And I'll start with the link layer. Okay, so we're looking at these layers over here, and particularly since we want to be focused on ROS, we're going to focus here and more in detail in this particular box as the first step. So problem is that in a common robotic setup such as this one, you may have a robot controller and then a couple of actuators plus a sensor that's somehow feeding the robot with useful information for just developing whatever behavior it needs to. Point is that if we start seeing how at the link layer the delays start basically spreading, we see that in some cases the delays, the latencies, go up to 2 milliseconds, and this is only due to congestion at the linked layer. So we've been working on trying to fix this problem. In particular, we've used a set of technologies or standards, better said, called time-sensitive networking that extend Ethernet, traditional Ethernet, to basically make it real-time capable. In particular, here we're using something called the time-aware scheduler, TAS, and using the TAS, we're able to basically lower the latency and restrict them quite substantially, about 3 orders of magnitude, actually. So we've gone from 2 milliseconds down to the microsecond level, which to us was a very interesting point. By the way, this has been done in collaboration with a number of different partners, among them Xilinx very actively, which we're very happy about. The next problem we tackled was actually the Linux networking stack, because it's just not necessary to have a real-time operating system, but also to have a a networking stack that somehow correlates fine with that. We ourselves use Linux, and that's where we focused and what I will basically describe right now. Without getting into too many details, the Linux networking stack actually has a huge amount of possibilities. It gives you a lot of flexibility, and actually you don't need to patch so much. You just need to configure your Linux setup appropriately. There's a paper over there where we actually described how we attacked this problem. And to demonstrate basically the capabilities of our optimizations, we basically designed this setup. So we basically have a client written in C and a server written in C, optimized for real-time deadlines, and have 4 different configurations. The no RT corresponds with a vanilla kernel, so just the usual Linux kernel. Then we apply the preempt RT patches, but we stay there. We don't optimize things to match. We certainly don't optimize the networking stack. Then the next one is one where includes preempt RT patches plus some optimizations on the networking stack. And finally, we do all of the previous things, plus we isolate the computation to a single core. With these 4 options in mind, we start measuring. If we have an idle system, and by a system I mean, since we are focused on modularity, all of the things you will see have been run on an embedded device, on this one particularly, this tiny guy. And this tiny guy is actually able to, when it remains idle, so there's no stress in the processor, neither networking stress, besides obviously the packages required for measurements, we get something close to below, let's say, not close, but below 2 milliseconds, which is somewhat acceptable, even with the vanilla kernel. So that was okay. Now if we start stressing this embedded device, then things start exploding with the traditional Linux kernel, with the vanilla kernel, and certainly we cannot use that. So we can see how applying the preempt RT patches, we get below the millisecond level. And again, remember, this is 2 ways. This is the ping pong test that I just described earlier. So if you just want to see them one way, you need to divide it by 2. Anyhow, just applying preempt RT patches does a pretty fine job. We can see some overhead when we use some optimizations on the networking stack, and also, let's say, when compared to just the preempt RT patch kernel, we also see some overhead when we isolate things in a single core. But the real value of doing such optimizations can be seen here. Now we basically introduce traffic. And what happens is that neither basically the vanilla kernel, neither the normal kernel are able to remain, let's say, stable. However, when we do apply on top of the preempt RT patches networking optimizations on the networking stack, we indeed are able to get the responses we want. A both-way response below 600 microseconds. That was a pretty good result for us. And everything, again, ran on this tiny device. So that meant we could do quite a lot of stuff and respond to a lot of industrial requests we were getting at the time. So the next thing we looked at basically was, all right, so we have these results now. How does it work if we put ROS on top? Because we were expecting certainly some, let's say, overload and some additional delays, but we wanted to be exact and precise on what did imply to get into ROS2. So we look at this, and our setup now is basically one where we used a robot controller designed for doing real-time control with manipulators. We isolated basically the test to a particular device like this one within a robot, and we designed a publisher and a subscriber that, similarly to previous tests, basically did a ping-pong. We're doing this, by the way, because we assume the worst. We assume there is no synchronization. And that way we can measure T1, T2, just make difference, and that way we get the latency. In this particular case, we did these tests using 3 different DDS implementations, just to make sure that in a way we did not stumble upon a buggy implementations or one with issues. With the system idle, now we see that the latencies are, well, somewhere below 5 milliseconds. So, and this, by the way, is this device without any optimizations, neither in the kernel nor in the Linux networking stack. Now, what happens if we overload the processors, the general purpose processors? Well, things just start exploding, and this is not usable, basically, on industrial applications. So we start putting basically all of our previous results on practice, and we see how an idle system does pretty reasonably, an overloaded system does fine so far, but we didn't want it to just stay there. We said, all right, now we have this, which is stable, let's start putting background traffic on it. With 1 megabit per second, still remains stable. With 40 megabits per second, remains pretty stable, but unfortunately, if we put 80 megabit per second, things start breaking apart. And the reason is because the Linux networking stack wasn't able to react on time. So we've been working already for quite a few months on this with the maintainers of the networking stack of Linux. We are hoping to basically release some patches that will hopefully get upstream, but this is anyhow a problem that the community is well aware of and something we're trying to, in a way, address and open source. Following up with basically the latencies with ROS2 is time synchronization, because I said before that we assumed the worst, but of course we didn't want it to leave aside. Synchronization is a tremendously important problem to deal with real applications. So we used a similar setup such as the one explained before, and we were able, by using PTP in a distributed manner, so PTP is running on each one of these tiny devices, to obtain sub-microsecond level distributed synchronization, which was to us pretty remarkable at the time. Without this synchronization, we could see how latencies sometimes exploded, especially if we played with the system, overloaded it, put it different, let's say, pain points into the network. We could see how basically latencies went way up, offsets particularly, sorry, in this case, up to actually 100 milliseconds, which I think was the complete period time we were using. If we use PTP, then things get constrained. And in our experiments, below 3 milliseconds. With all of this information, we were rather satisfied. We had basically qualified our embedded device to do real-time, at least soft real-time or firm real-time in some cases. And we basically were happy at that time. I think this happened quite a few months ago, actually a year. We got all of these results and then we started publishing them. But we asked ourselves, and we've been asking ourselves over the last period, can we actually do better? And we believe we can. And that's how we basically started with this AI group. We started with our AI research about a year and a half ago. And basically we did so with the idea of saying, okay, so now we have the modular way of building robots here, right? Where we have somehow eliminated the integration effort. But there's still this huge box here, number 3, right, that shows the task of programming robots. And of course, we will always need to program robots to one way or the other. And ROS has done a fantastic job on that. But can we actually simplify this a bit? And so what we did, we started doing, was actually using these reinforcement learning techniques to try to, rather than programming robots, training them. So basically defining the task that we wanted them to accomplish, typically through a reward function, and just throwing it out there to the cloud or locally if you had enough computation power in your offices, and just let it train. The whole idea is basically around taking observations, training, and deploying it automatically, which would potentially allow us to serve clients and eventually, if we could train fast enough, basically change some minor setups on our deployments and get the robot retrained online, on the edge, hopefully, in the factories themselves. Now, are we ready for doing so? So after 1 year and a half, maybe a bit more of research, and probably more than 40 PMs dedicated to it, I'm sorry, and we said this also at ROS-Con, we are sorry to say that we ourselves are not ready. We've participated in state-of-the-art conferences, we've contributed, but still our results, we've moved it. Actually, the previous speaker just shared a few things about it, are better than the ones we obtained with reinforcement learning techniques, a variety of them. We still keep working, and that's why we are releasing actually some APIs, 3 levels of APIs, actually. The first one in blue, which is fully ROS-based. The second one in purple, it's built on top of ROS, but implements different reinforcement learning techniques, basic ones such as PPO, TRPO, but also more complicated ones. The ones at the top are hierarchical learning techniques, which basically build on top of the other ones and build multi-level networks of reasoning. But that's just one way. Again, we are investing on that because we believe it has potential, but certainly our objective is to deliver and get results out there with our modularity technology, and that's why we basically started building layer 3, which unfortunately right now is not public. It will become soon, hopefully, and that layer is basically aimed to simplify the task of basically developing applications with modular robots. Now, when we asked ourselves if we could do it better, we just didn't start working on AI. We also wondered if, besides the technical aspects that I just covered, among many others we faced, are there any other things we are leaving aside and are relevant for modular robotics or modular robots? And indeed, they were. One of them was interoperability, which is a key thing to simplify the integration effort. And that's how we started basically building this project called h-ros, which stands for Hardware Robot Information Model, which is basically a meta model for robots. And as you can see in the picture above, it allows you to basically produce artifacts for communication in robotics from meta models down to the implementation itself. To try to explain this a bit better, let me do it the other way around. Let me start from what most of you probably know already. So this is the message definition of a camera, right? The ROS one. Point is that if you start browsing across the different packages in GitHub, Bitbucket, or whatever you guys use, you will see that depending on the developer or the manufacturer, they have different interpretations of this package. They modify this field, they add this other thing because my camera has more stuff or this other topic. And so that creates tons of issues on interoperability. We're working a lot with manufacturers and we've seen this over and over and over again. So we said, okay, roboticists hopefully should not touch the implementation. They should generate it. And this aligns very well with the model-driven engineering approaches that many people is encouraging within Industry 4.0 and the overall industrial landscape that's happening here in Europe. So if the message needs to be generated, okay, let's have it generated from a more abstract representation using XML. But still, this is platform specific. This is specific for ROS. So what we can do is actually we can get agnostic to the platform. We can support ROS or ROS2 or OPROS or YARP. We have users doing this actually. And we do so by just some data mapping, just some simple data mapping that can allow for this abstraction to move forward. And then at the top, we can build meta models in a rather simplistic manner. And just with some tooling that we are about to open source and document, by the way, documentation is yet not ready, we can actually make the whole process seamless or easier, so to speak. This whole effort has been supported and funded by the European Union through the ROS-In project. And frankly speaking, we're very excited about these results and hopefully many of you can use it. We're also in conversations with the Open Robotics to basically try to get this into the main ROS packages, maybe even into Amend or Qualcomm now, so that basically it gets auto-generated for all ROS-2 packages. And we're also looking at whether we can somehow transfer the intellectual property of the project to maybe Open Robotics or some other organization here in Europe to make sure that there's also some sort of coordinated compliance towards interoperability. And this is relevant, and certainly only a company like ourselves can do it. So maybe Open Robotics can certify that you comply with the messages or with the abstractions for being a camera or whatever, but we believe this is a really important topic when it comes to modularity. And again, our team is very committed to work on it, so we invite everyone interested to jump in and contribute. So it indeed seems that with all of this work, modularity indeed reduces the integration effort. Now, our solution had it in my basically hand. The whole talk is this tiny box. This is our solution for modularity. And we basically wrapped all of this in a stack that goes from the hardware architecture up to the application level with optimized ROS client libraries for real-time response. Our vehicle is basically this tiny box that typically gets integrated in hardware, robot hardware, in this manner. So we work with manufacturers. In this particular case, this is Hand Robot, a Chinese manufacturer of robots. This is a joint, 2 degrees of freedom. And so what we add basically is our SOM, the system on module of h-ros. And by doing this, we basically managed to get ROS-2 natively running on the actuator. So the actuator itself is publishing, it's subscribing, it has parameters. So you actually, as a developer, don't need to SSH into it anymore. You need to fine-tune things. Of course you could, and we are developing tooling to facilitate things such as configuring security, setting up certificates on hardware, setting up things such as fine-tune parameters, things like those which we understand are needed. But still, the complexity of needing to SSH into it, install ROS, or ROS-2 in this case, cross-compile things, we've seen tons of issues about this. We fixed that problem by directly working with manufacturers. This is one of the many we've been working on, and one we're very proud of. But again, everything starts from our vehicle, which is this SOM, the system on module. Using the SOM and partnering with manufacturers, we've actually managed to come up with the first modular, industrial, and collaborative robot. We're very proud to present MARA, the modular articulated robotic arm, which is basically now available for pre-order for 15,000 euros, which we believe is a reasonable price, more than reasonable for a modular robot that has industrial capabilities and has ROS-2 on every single one of the joints. So with this, I invite you all to basically dive into modularity, and I open myself to your questions. Thank you.